So if you need notes or video from Thursday, what would that have been? 10/11. Use the notes and video from the night class on Wednesday, 10/10. Okay. All right. So last time I just started talking about Newton's second law. The new topic was 2D kinetics of particles. And the big result, the big equation, this is the most important equation in this whole semester, is Newton's second law. That's abbreviated by me, N2L. And it says that Fnet, which is a vector, is equal to the mass times the acceleration. And now we have to be careful about what all of these things mean. So Fnet is the, I was going to say total, but let me say the sum of all the force vectors acting on the chosen object. This idea of a chosen object is going to be really important. We're going to make a lot of, well, not just a lot of effort. If you're not careful about defining a chosen object, being clear about what the boundaries are, you're going to get things wrong using this equation. The idea of a very specific chosen object is a key thing. So Fnet is the sum of all the force vectors acting on it. M is the mass of the chosen object. And A is the acceleration vector of the chosen object's center of mass. And one thing to notice about this, I mentioned this last time, is that since mass is always positive, the acceleration vector and the force vector are always in the same direction. So Fnet and the acceleration vector A, that's the acceleration of the object's center of mass, are always in the same direction. And so, you know, in lab, we're doing all these exercises to help visualize the direction of the acceleration vector. If you can visualize the direction of the acceleration vector, say like in a lot of cases, we'll know that the acceleration acts within a 90-degree range. If you know that about the acceleration, you also know that about the sum of the forces. That doesn't necessarily tell you the directions of the individual forces, but it it can be useful to know, to be able to picture the direction of the total, the sum of the forces. Okay, and then I defined mass, and that was a pretty simple thing. And we think about mass as a resistance to acceleration. And now we have to start talking about forces, and that's going to be a long process. So I'm going to call a force a vector representing the intensity and direction of a push or a pull on an object. And one thing that's going to be useful, and it's going to be an important thing to get used to making yourself come back to, is that every force that we deal with fits into one of two categories. Forces are either first, the weight. And I think I mentioned last time that weight is really fits into a category of other things. But the only one we're going to deal with in this class is weight. That's why I'm writing it like that. But the category it fits into is field forces. And that includes magnetic forces, electrical forces. We're just not going to deal with that kind of stuff. It's not really any harder. We're just not going to do it. And then once you've dealt with the weight of an object, the only other type of force you have to deal with are contact forces applied by outside objects. So these contact forces, and actually let me reword that, contact forces applied by objects that are touching the boundary of the chosen object. Okay, and so there'll be problems that are, problems can get sort of complicated. And a lot of times when you first look at a problem, it'll look really complicated. The way to approach simple problems too, but especially as they get more complicated, is to remind yourself that all you have to account for is the weight, and we'll talk about how to do that. And then just mentally go around the boundary of the object, looking for places where the outside world makes contact with the boundary. Anywhere that there's contact with the chosen object at the boundary, there's going to be some kind of force there. And we'll talk about how to account for individual forces. Once you've gone around the whole boundary and accounted for every place that the outside world is touching, you know you're done. Okay, so that's sort of you look at a problem and you're like, oh my God, there's a million things going on here. Well, if you remind yourself of this fact, you can sort of keep track of it. Like, so for example, let's say there's some mud and there's a truck and there's a pig on the back of the truck. And there's a giant bird standing on the pig. Like that bird in Up. And there's a man trying to pull the truck out of the mud with a rope. And there's a cowboy trying to lasso the policeman standing in a helicopter. Okay, let's say that's enough for now. Let's see, standing in a helicopter. What are the forces on the pig? Okay, well, there's a million things going on in this picture, right? You look at it and it looks sort of like chaos, but first you have to account for the weight, and then go around the boundary of the pig and look for where the outside world, the non-pig world, is touching the boundary. The truck is touching the pig, so there's a force on the pig by the truck. There's a force on the pig by the bird, and no other forces are acting on the pig, just those three. Okay, and it can mess with your head a little bit sometimes if you don't think about it this way, because you're like, well, what if this guy gives a big strong jerk to this rope? That's going to move the truck, and that's going to change the force that pig feels, right? So this guy with the rope must be applying some kind of force to the pig. But all that happens when this guy makes a jerk on the rope, it changes the force that the truck applies to the pig. It's still just a force applied to the pig by the truck, okay? And so we're going to be very systematic about that. And if you use only those three forces in the equation, you'll be able to calculate all that stuff, including all the secondary stuff that comes from, okay, well, no, what if this guy accidentally lassos the bird and it pulls him along? All that secondary stuff is still going to come into the problem as we go. But when you isolate the pig, it's only those three forces, the weight and the two contact forces. Drew that picture. It better be in your notes. Okay, so the first thing we have to talk about is how to account for the weight force. That's the simplest of these. You always treat it the same way. And another way to say the weight force is the force on the chosen object applied by gravity. And we're going to be able to figure this out just based on the stuff that we know so far. So to do that, let's think about, let's calculate the weight force applied to an object of mass m. Okay. And the way we're going to do that is imagine that this object with a mass m is in free fall. Okay, so free fall. This is going to be really useful because there's two things we know about an object in free fall. So two key facts in free fall. The first one is that the only force acting on an object that's in free fall is the weight. That's the definition of free fall. And what else do we know about an object in free fall? That's right. The acceleration is 9.81 meters per second squared down. Okay, so this is our object with mass m in free fall, and it doesn't matter whether it's being shot out of a cannon or falling straight down or being shot straight up into the air. As long as the only force on it is gravity, we know that the acceleration is 9.81 down. And I'm going to choose a coordinate system. And I'm going to choose the y-axis pointing up, like I think I always have in free fall problems. The chosen object is the thing that with the mass of m. And so in components, what's its acceleration? It's 0 for x, and then negative 9.81 meters per second squared. The mass is m, and we don't know anything about the force, so I'm going to write that. So here we go to Newton's second law. So if we include all the forces acting on this, all that is the weight force, and I'm going to call that Fw, for the weight force. I'm going to break it up into an x and a y component. We don't know either of them. That's what we're trying to calculate. And that's equal to the mass of the object, which is m, times the acceleration of the object, which is 0 for x, negative 9.81 for y. And now we can break this vector equation up into two pieces, an x equation and a y equation. The x equation says Fwx is equal to m times 0, so 0. And the y equation says Fwy is equal to negative 9.81 m. Or we could also think of this as negative mg, where g is a constant, negative 9.81 meters per second squared. So now if I write this as a force vector, the force vector is Fw vector, and it has components of 0, negative mg. That's just straight in the negative y direction, so we could also write this as a vector of mg in the downward direction. Either one of those is fine because it gives everything you need to know about a vector, a magnitude, and a direction? Okay, so what that says is that, the weight acting on any object is proportional to its mass. All right, so now I need to say something. This gets really confusing when you first start thinking about this in relation to common misconception number 1. Okay, so how does this relate to common misconception number 1? Yeah. Okay, so what this says is that, so common misconception number 1, from that, what we know is that if there's no air resistance, all things fall with an acceleration of 9.81 meters per second squared down, regardless of mass. That's the true version, right? This is so talking about common misconception number 1 led us to this result. And now, so remember the video we watched showed in a vacuum chamber where we got rid of any air resistance, you drop a bowling ball and a feather at the same time, and they both accelerate the same, hit the ground at the same time. And now we're told that gravity actually pulls harder on things that have more mass. WTF? So how does that? So how do those square with each other? Those are both totally true. I'm not trying to trick you or anything. Those are both true, but it can be a little confusing. Okay. And the answer is that, okay, everybody's sort of absorbing what I'm talking about here. Like, I spent all this time trying to tell you that in some way gravity treats every object the same no matter what its mass is. And now I say what seems like the exact opposite, that something with more mass gets pulled harder by gravity. But here's how it all works together. Remember that mass is resistance to acceleration. So an object with more mass is harder to accelerate. Okay, remember the picture I drew of the giant football player about to run into the little football player? And I said that the little football player is going to accelerate a ton. The big football player is not going to accelerate much. In other words, in order to make the big football player accelerate as much as the little football player, you have to apply a much bigger force to the bigger person. Okay. Um, so in order to make um, an object with a large mass accelerate the same as a small mass, you have to apply a bigger force. That's the key thing here. Okay, so the weight force applied to a feather in the vacuum chamber, they both accelerate the same, but it's a much smaller force that gravity applies to the feather to make it accelerate down at 9.81. It has to apply a much bigger force to the bowling ball to make it accelerate down at 9.81. But this idea that the weight is bigger for the force that gravity applies to bigger things is larger than the force it applies to smaller things is why you can weigh yourself on a scale. What you really want to know is your mass, but when you stand on a scale, what you're measuring sort of indirectly is the force that gravity applies to you. That's not your mass, but it does go up as your mass goes up or go down as your mass goes down, and that's why it tells you useful information. Anybody have any questions about this? Okay, so now we're going to use what we know about, and I should say, so we did this to calculate the force that gravity applies to an object in free fall. But this is always true, no matter what the object's doing. Gravity applies the same force to a single object, no matter whether it's rolling or sitting or being thrown in the air, or, no matter what's happening, the weight force is the same. Gravity always applies that same force. It's not true that the acceleration's always the same. For a bowling ball to be accelerating down at 9.81 meters per second squared, it has to be in free fall. If it's sitting on a table, it's not accelerating at all. But whether it's sitting on a table or in free fall or anything else, gravity is pulling on it at mg down. Okay. So now let's see if we can sort of piggyback on what we know about the weight force to calculate other forces. So example. Negative is a direction, and so that depends on what you choose as your coordinate system. So really what weight is always down. Yeah, it's always the same direction as, and it's always the same direction as the free fall acceleration because that weight force is what makes something accelerate down. So yeah, it's not always negative. You could put your positive x direction down if you wanted, and then it would be not, positive mg and then 0 for y, but it is always down. Yep, it has a direction. Yep. Okay, so let's say that okay, so here's the floor, and there's a bathroom scale on the floor, and a man on the bathroom scale. Didn't I? What did I say I was going to do? I'm bored with that one. Oh yeah, the one of calculating the force? That is the answer. This is the answer. Every single problem you do, you're going to use this depending on the object's mass. Yep, that's right. So in the next one, I'll put numbers in. Okay, so here's this guy on the scale. Let's say the mass, just to make it a nice round number, let's say the mass is 100 kilograms. What's the force the scale applies to the man's feet? Okay, well, our chosen object is just going to be the man. And so let's start compiling this information. What are the forces that are acting on the man? The first one is the weight. That's always going to be in there. And so that's the mass of 100 times 9.81. If you're using SI units, that's what I'm usually going to use, pointing down. And so 100 times 9.81 is 981. So in this coordinate system, that's in the negative y direction. So it's a vector of 0, negative 981. Kilogram meters per second squared is newtons. And then there's one other force too. Now that we've dealt with the weight, now we just imagine going around the boundary, looking for places where the outside world makes contact with this chosen object. That's the only place. So the only contact force is the force on the man by the scale. And for now, we're going to assume we don't know anything about that. And so I'm just going to treat that as an unknown x component and an unknown y component. That's the least you can know about a force vector. Okay, you don't know the direction, you don't know the magnitude, you don't know x, you don't know y, you don't know anything. So I'm going to call that force scale, and I'm going to break that up into fsx and fsy components. Then the mass, m equals what we're isolating, the chosen object is just the man. It's not the man in the scale. It's not the man's torso and his left leg. It's the entire, like, I just did like an hourglass figure, but that's not what I meant. It's the entire man enclosed in like our imaginary like shrink wrap. And so the mass of our chosen object is 100 kilograms. And the last thing is, do we know anything about the acceleration? All he's doing is just, it's not free fall anymore. 0. He's just standing there. He's not moving. At every instant, his velocity is 0. And if the velocity isn't changing, you can't have acceleration. So the acceleration vector is 0, 0. And so now let's put this together. So Newton's second law says 0, negative 981, that's the weight force, plus the unknown force applied by the scale, that's FSX, FSY, is equal to the mass of 100 times the acceleration of 0 and you can break this up into an x and a y equation. The x equation says 0 plus FSX is equal to 100 times 0, so equal to 0. The y equation says negative 981 plus FSY is equal to 100 times 0. So the equation tells us that FSX is equal to 0. Even though, you know, that's sort of a long name for that variable. That's just a variable, so you solve for that the same way you solve for x or whatever. And the y equation says FSY is equal to positive 981. So if you put this together, the force applied by the scale, Fs, is equal to 0, 981. Units are newtons. And what direction is that vector? So, well, let's draw a coordinate system. What? Up, that's right. So, yeah, so so remember that the components of a vector, any vector, are the same as the coordinates of the head of the vector when the tail's at the origin. So plot this point. You go 0x, positive 981y. Put the tail at the origin, and then this is the vector. And it has a magnitude of 981. So another way to say this is 981 newtons up. Okay, so have you ever wondered? Probably not. Have I ever? Probably not. But if you think about it like a philosopher, like, whoa, man, how does this bathroom scale know how hard gravity's pulling on me, man? You know, how does it know? Well, the answer is we pretend like we treat it like the bathroom scale is telling us how hard gravity's pulling on us. Really, what the bathroom scale is measuring is how hard it's pushing up on us. Okay, that's all the bathroom scale can measure. It just knows how hard it is to push to keep us up. But as long as the setup is like this, where you're standing at rest with no acceleration, and the only forces acting are the weight pulling down and the bathroom scale pushing up, those have to be equal and opposite. You know, you can make bathroom scales give you the wrong answer about what the weight is, how hard gravity is pulling on you. One way you can do it is stand on the scale and lean on the counter. Then there's a third force happening. The counter is also pushing up on you. And then you can't assume that the force of the bathroom scale and the weight force are equal and opposite. So it doesn't tell you your weight. Another one is if you jump on the bathroom scale, and as you're jumping up and landing, you're accelerating. Your acceleration isn't 0, and that changes the answer. Mm-hmm. Yeah, the guy will be pushing down, right? Yep. And the ground will be pushing up on the scale, and and the weight of the scale will be pulling down. Yep. Then we have three things, so we can't use this approach yet, but to think about it. But yes, that is what's happening. Right, there's two things that we don't know going into it, right? Oh, but sorry. So we haven't talked about this officially yet, but unofficially, what do you think? So we learned that the scale is pushing up on the man with 981 newtons. Any guesses on how hard the man's feet are pushing down on the scale? The same. Yeah, 981. Yeah, and that's how it is. That's Newton's third law. That's probably the second most important equation in this class, and we'll get to that in the next week or 2 weeks or something. Okay. Mm-hmm. Yeah. Mm-hmm. Why are you adding that to get FSY is equal to 981? It's just like if you had an algebra 1 equation that said negative 981 plus x is equal to 0. Oh, I understand that algebra. I'm saying how you set it up. Oh, over here? Second one up, all the way up. Okay. Like, why add that? Because the net force is the sum of all the force vectors. So you sort of list out the forces that you're dealing with. One is the weight, and the only other one in this case is the force that's applied to the feet by the scale. And then you just add those vectors together. So get them into component form and then add them, and that's Fnet. Yeah, let me write that here. So these two added together are Fnet. That's what Fnet means. You're just adding up all the forces on the object. Any other questions? Okay, so now here's a weight loss idea. We're always looking for easy ways to lose weight, and this is the easiest way to lose weight. No, that's a horrible, hard way. That's true. I think this is easier than that. Okay, so here's the second example. So now it's going to be the same setup. There's the scale. There's the man. And the man's mass is still 100 kilograms, but now the scale is on an elevator that's accelerating down at 2 meters per second squared. Now, I should say, like, when you're in an elevator going down, you're not accelerating the whole time you're going down. You're not accelerating down. You're only accelerating while the velocity is changing. So, like, when you go down in an elevator, you feel that first second where your stomach you feel it sort of lift or whatever. That's while you're accelerating up to the speed, and then you hold the constant speed the rest of the way. So this only works for the first 1 second of a trip in an elevator. Okay, that's the sad thing. But now let's calculate the force that the scale, the force that's applied to the feet by the scale. Okay, so let's think through it all again. So first, the forces. What's the first force? This is the easy one. Weight, yep. And the weight is always the same. It's mg pointing down. So that's going to be, if our coordinate system is oriented like this, this is going to be 0, negative 981, just like it was before, newtons. And then what's the second force? It's just like it was before. You still just look around, even though he's accelerating, you still just look around the boundary for where there's contact with your chosen object. So the force on the man by the scale. And again, I'll call that Fs, and I'll say we don't know anything about the X or the Y components. We'll calculate both of those. So again, Fnet is equal to 0, negative 981 plus Fsx, Fsy. The mass is still 100. But this time the acceleration's different. What's the acceleration this time? Yep, it's in the negative y direction with a magnitude of 2. So the acceleration vector is 0, negative 2 meters per second squared. And now we just have to put all this together. So Newton's second law says the net force, 0, negative 981, plus Fsx, Fsy is equal to the mass times the acceleration vector. And we can break this up into two equations. The x equation says 0 plus Fsx is equal to 0. The y equation says negative 981 plus Fsy is equal to negative 200. So solve for Fsx, and that's 0. Solve for Fsy, and that's 781. So the answer is that force applied by the scale in the elevator that's accelerating down is 0, 781, or another way to say that is 781 newtons up. So he just lost 200 newtons instantly with no exercise. That's what we measured, is what the scale reads out. So, compared to pounds, I think it's about 4.25 newtons is a pound. Well, I know how to, so multiply 100 by 2.22. Could you do that, James? Well, 222, duh. Okay, so 222. So take 981 divided by 222. No, 222 divided by 981. And then multiply whatever you get there by 200. And what's that? Okay, he lost 45.2 pounds. And if you find a stronger elevator, you can lose even more weight. Actually, anybody have a guess for what the elevator's acceleration would have to be? So the more it accelerates down, the less the scale reads, until at some point it finally reaches a reading of 0. Anybody have a guess for what the acceleration of the elevator has to be for the scale to read 0 for the first time? Negative 9 point, well, yeah, it has to be the acceleration of gravity down at 9.81. If the thing you're in is accelerating down at 9.81, then you have the feeling of being weightless. And actually, that's what happens. I think a lot of times we get the sense that astronauts on space stations or whatever, that they're experiencing weightlessness because there's no gravity out there. But that's actually not why it is. They're still close enough to Earth to feel the Earth's pull, although it's reduced a little bit. I mean, the space station is in orbit around the Earth, so something has to be making it orbit, and that what's making it orbit is the gravitational pull. The reason they experience weightlessness isn't the lack of gravity, it's that the space station is essentially in free fall around the Earth at the same time that the astronauts are in free fall. And so they have that same experience of being in an elevator that's accelerating down at 9.81. So if they get on a bathroom scale, it says 0, just like you would here. If you're accelerating, so first of all, just be careful with that word, because one thing that's going to be tricky is mixing up velocity and acceleration in your head, and so faster is speed or velocity, but if you're accelerating more than 9.81, then you have the experience of accelerating up, like to you in the elevator, all of a sudden you feel like a gravitational pull towards the ceiling. And okay, now this next comment is sort of getting deep into the weeds, but some people, so general relativity recognizes that there's no way to tell the difference between a gravitational field and an accelerating coordinate system. And so basically, like if the elevator was accelerating down at 20 meters per second squared, it would be exactly to you as if you were in a gravitational field that pulled things toward the ceiling of the elevator. There'd be no way to tell the difference. No mathematical way, no experiment you could do or anything. That's Einstein for you. And I mean, that's kind of an interesting thought, but that's not really, that's not really why what he said was important, but that really is kind of like at the heart of all the calculations that he enabled with his equation with E equals mc squared. Any other questions? Okay. So the next thing we're going to do, and I'm going to stop here, but let me just set up for next time. So the next topic is going to be free body diagrams. And the idea of a free body diagram, I'm going to abbreviate them FBDs. But a free body diagram is just a systematic way to be sure that you're clear to yourself what your chosen body is. and to make sure you include all the forces acting on the chosen body. Um, and this is going to be an important thing. I will, and I'm not like alone in this. This is a sort of a general uh, way of approaching this. I'm going to require a free body diagram for every time you use Newton's second law. So you should think of there always being a one-to-one correspondence. Anytime you're going to use Newton's second law, you draw a corresponding free body diagram. Okay, and we'll get into how to do it and what the rules are for it and stuff, but it's going to be a helpful thing. I'll require a free body diagram for every use of Newton's second law. So we don't have school on Thursday or Friday, so enjoy MEA, and I'll see you on Tuesday. Oh, except for people who have lab. We do have lab tomorrow. Yeah, so if you have lab tomorrow, yes, we do.